we shall continue with Chapter 4 in Algebra 2. We have discussed in this chapter already exponential functions. And we have suggested the parent graph was this, and the other parent graph was this. And we had suggested previously that this parent graph models exponential growth, and this one models exponential decay. And the general equation for exponential functions was this. So we have talked about these previously, and in regards to examples we have talked about before is the compound interest formula, which is like this. So this is the amount of money after a certain time t, and P was the principal amount, the original amount that was put in. And R, of course, was the interest rate. And N, as I had suggested before, was the number of times the interest is calculated. How often interest is calculated. Now, and I suggested to get a reminder that this is the only term that's found twice in this equation, and T, of course, is the time. So this was a very specific example in regards to compound interest in the banking industry. And then I had suggested before that the general equation for exponential growth otherwise is like this. Okay, and the exponential decay was something like this. Okay, so today I like to give two specific examples of this, and I also would like to talk about specifically half-life equation, which is modeled slightly differently than this, and try to do this patiently so we don't rush through this, because I really like you to understand these two concepts. Half-life equation. Okay, because this will be a recurrent concept in different sciences. So let's do an example. These I'm just going to get from the textbooks. Our textbook, and example number 4 says, this is on page 238. A snowmobile, yeah, good boy and take notes, it costs $4,200. And the value depreciates or decreases by 10% each year. Okay, so somebody buys a snowmobile for $4,200, the value is going to depreciate by 10% every year. The question is to write an exponential decay model giving the snowmobile's value y after certain t years. So this is easy enough. We said exponential decay models are like this. Now the book uses a instead of b as a variable here, and that's easy enough. You can substitute that as long as you understand the concept. So the amount, the value of the snowmobile after a certain period of time t is going to depend on the initial value, which is here. This is the initial value, and the rate of decay, which is here. Okay, so let's write that. Rate of decay, so to speak, or depreciation. So this is going to be, the initial value is 4,200 times 1 minus 10% is 0.10 to the t. And you can simplify this as y equals 4,200 times 0.9 t. So this is the equation for the value of the snowmobile as a function of time. Okay, so they ask us two questions here. First, I want to find out how much the snowmobile is worth, let's say, after 3 years. So here's the formula that we have derived. Now, appreciate that this is a and it's less than 1. Therefore, this should be modeled by exponential decay. So there'll be some initial value here, which is 4,200, and the value will depreciate in an exponential form like that, exponential decay. So after 3 years, when t is 3, the value of the snowmobile will be this. Let's try to find out. So it's going to be 4,200 times 0.9 to the exponent of 3. So it will be worth $3,061.80. 61. That's how much it will be worth after 3 years. Okay. So this is an example of exponential decay, and this is also in cars. You can, if somebody buys a car for $22,000, let's say, the value of the car depreciates by a certain percentage every year. I don't know how much percent it is. If it's the snowmobile, it's going to be 10%, and you can figure out how much the car would be worth based on this formula. It would be 2,200 or 22,000 times 0.9 times t in years. Okay. That's another example. Now, another example I wanted to do was this that was given on page 240. It's a problem that's given. And this we did in class, but I just wanted to, it's so important that I really wish you to appreciate it. It says that when a person takes a certain dosage of ibuprofen, so they're taking medications, ibuprofen, okay, and they take a certain amount of it, I, in milligrams, okay, the amount of medicine that remains in the blood after a certain amount of time is modeled by this equation. Okay, so here is the initial amount that the person takes, and it is the amount of the medicine remains after a certain time. So amount of medicine in blood. Watch this. In blood after a certain time t, and t is time. Now again, I'd like you to appreciate that this value is less than 1. Okay, so this will also be an exponential decay model. Okay, starting with the initial amount and going down like this. Okay, so this will be modeled with this parent equation. Okay, the initial amount will be in the blood will be this. So how much of the medicine will be there after 3.5 hours? Okay, so if a person takes initially 325 milligrams, they say, how much of it will remain after, let's just say, 3.5 hours? Okay, that's easy enough. So let's do that. So 325 times the quantity, 0.71. If I did that right, to the exponent of 3.5. So 98.01. So this is about 98.01 milligrams will be left in the blood. Okay, so these are two examples of exponential decay. Now I wanted to talk about a third concept here, and that is half-life. Okay, so for example, carbon-14 is frequently used to date ancient articles, or other radioactive material is used to date things. Okay, so I wanted you to understand this as a concept, but also as an equation. So look at this, for example. So for carbon-14, if there's a certain amount of stuff in the beginning, when we say its half-life is a certain number of years, it means in that first half-life, half of the material will be uh, uh, no longer radioactive. Okay, so half the material will be gone, half the carbon-14 will be gone. In the second half-life, half of the remaining will be gone, half of this much will be gone. And the third half-life, half of the remaining will be gone. Okay, so that's the concept of half-life. We try to illustrate that here. Okay, so let's just say initially, let me put it all. Okay, there is this much amount of material there. In the first half-life, half of it, okay, will have deteriorated, and half of it will remain. Okay, and the second half-life, half of that would have disintegrated, and half will remain. And in the third half-life, half of that would have deteriorated, like this, and so on and so forth. Okay, so you can see how this is a exponential decay phenomenon. So let's pick a color here. Let's pick blue. See, like this. I didn't do a very good job, but you get the idea. Let me try to do it the artistic way. Yeah, I like the artistic way. Kind of gives you, yeah, like this. Okay, so that's the concept of half-life. The formula for half-life is this. Okay, this time I'm going to do it the way the book does it. The amount of stuff remaining, this is A remaining, depends on how much stuff you started out with. You can use, in case of the banking, we use P, right? You can use whatever symbol. Here they use many times A0, means amount at initial time 0. Okay, so amount of stuff remaining at any given time is depends on the initial amount, okay, times 1/2 to the exponent of time over the half-life of a substance. Okay, I'm just going to here use a substance as an example. I'm just making it up. Let's say you have a substance that's half-life is 30 days. Okay, that means in 30 days, okay, it will take 30 days to go from here to here. Another 30 days, half of it will be gone. Another 30 days, half of it will be gone. Another 30 days, half of it will be gone. So it will take 30 days for half of the substance to disintegrate or decay. So half-life is 30 days. So if my hypothetical substance, that will go over there. But you might say, okay, wait, this looks a little different here. What's going on? This doesn't look like a typical exponential function formula, right? So the amount of stuff remaining depends on the initial amount, we're familiar with that, times 1/2, times to the exponent of time over the half-life. So I want you to get a little bit better understanding of this formula. So I'm going to kind of derive it for you. So let's say the initial amount is this. This is the initial amount. At time 0, you have some, let's say, this much amount of stuff, and the amount of stuff you have is A0. Amount of stuff at time 0. Okay, this is at when the half-life is 0. There's no half-life has passed, right? Now, after one half-life, okay, now the stuff that will be remaining will be this much, half of the original amount, okay? So this will be after half-life is 1, okay? So after one half-life, this is how much this stuff will remain. After the second half-life, it will be half of that remaining. It will be half of this. All right? Correct? That at the second half-life. And after third half-life, it would be half of this that remains. And there would be, this is how much that will remain after the third half-life. And just one more time, after the fourth half-life, okay, it would be half of that much that would be remaining. Right? That makes sense. That's pretty reasonably clear. So this is after 4 half-lives. Okay. Now, if you observe this, what's happening here is that basically you're multiplying by half every time. Right? So that's what this graph is saying. Right? So this graph is saying that one half of remaining, half of that remaining half. So basically multiplying by 1/2. Okay? So the amount of stuff that remains after certain half-life, let's say, will be the initial amount multiplied by 1/2, okay, to h, the number of half-lives. So when h at the beginning, which h is 0, when h is 0, you would get this. When h is 1, you would get this. When h is 2, you would get this, right? So this formula that I have over here is basically a formula that represents the phenomenon that's going on over there. Okay, now for example, let's say I have 100 grams of this whatever material I'm talking about. I want to know how much, and let's just say half-life is like 30 days, okay? How much of the material will remain after 3 half-lives? So I have, initially I had 100, and that's pretty easy enough. I go like this. After 3 half-lives, let's figure out, I start out with 100, I use grams, I have 100 grams, and 0.5 has half to the exponent of 3. After 3 half-life, it would be 12.5 grams remaining. Okay? Now, after, let's just say, 7 half-lives, it would be like this. So let's just see what that comes out. 0.78125. That's how much stuff will be remaining. But people are interested after how many lives. Now, what if I ask you this question? How much of the stuff will remain? How much will remain? Not after half-life, but after after 60 days. Okay, how much will remain after 60 days? If you look at this formula, there's nothing you can plug in over here, right? You can plug in only half-lives over here, right? Correct? So, excuse me, let me fix this. So, what am I going to do? I want to know how much it remains after 60 days. Well, we're going to have to figure out how many half-life that is, right? Well, you say, okay. Oopsie daisy, I didn't want to do that. I just did all that work. So now look, 60 days divided by the half-life, okay, is 30 days. That's 2 half-life. Then I plug that in over there. So if I do this for just 2 half-lives, I have 25. The answer is 25. Okay, so let me just reiterate this problem. Initially, I had 100 grams of stuff, and I have said the half-life of the substance is 30 days. I have derived this formula for the amount of stuff remaining after a certain half-life. Okay, and then I said how much of the stuff will be there after 60 days. Okay, well, you said that's 2 half-lives, and you put 2 over there. If I said, how about 90 days? Okay, well, that's 3 half-lives. How about 120 days? Well, that's 4 half-lives. How about 100 days? Right? Well, that's going to be 100 divided by 30, right? That's going to be 10 over 3 half-lives. Right? So, right? So you can substitute this easy and write the formula in terms of days. Okay? So the number of days or time divided by the half-life of the substance will give you how many half-lives have passed. So this is number of days or time or years, whatever, divided by half-life. This gives you how many half-life have passed. So, right? And that you substitute over there. And this is the reason why the half-life formula looks like this. T divided by H. Okay, and I hope you appreciate this. Okay, now if give you another example, a real life example. It says the half-life equation for chromium 51 is given by this equation. T over 28. Okay, where half-life is 28 days. Correct? Okay. So how much of if somebody has I'm making up 100 grams, let's just make it 200 grams of chromium. Okay. And how much of chromium will be there after, I don't know, let's just say 100 days. Okay. So let's do that. So this would be 200 times 1/2 to the exponent of 100 divided by 28. Okay, I do that right. So it would be 16.82, approximately 16.82 grams left. Okay, so here I reviewed exponential decay formula, and also we studied a little bit about half-life, decay of radioactive isotopes, and that formula is this. Okay, where A is the amount of material left after a certain amount of decay, A0 is the initial amount of material, T is the time, and H is the half-life of the material. Inshallah, I hope that was instructive. Until next time, then, assalatu wassalamu ala rasulillah, alhamdulillahi rabbil alameen.